Hi students, in the previous session we have seen about Gauss law and Coulomb's law. In Gauss law, how this is applicable to find the electric field due to a point charge, charged plane sheet and a charged wire. In the today's session we are going to see about inverse square law and its application to various things. Let us have a small introduction about the inverse square law. If we see that the number of physical properties will get smaller value when it is farther apart from each other. For example, if we consider force between the two charges, the force is the physical property and it will be getting smaller value if the distance between the two charges is going apart and apart. Then the intensity of the physical property decreases with the increase of the distance. That's why we are telling that the intensity is inversely proportional to the square of the distance. For an example, from the radioactive source, if you are traveling, then the radiation exposure will be decreasing. That means that if the distance is 2x from the point radioactive source, then the decrement will be 1/4. If the distance is 10x, then the decrement of the radiation exposure will be 100. Then it can be represented as x is proportional to 1 by d square, where x is the radioactive point source and d is the distance of the point from the point source. Now, this inverse square law is applicable to various physical properties. I am going to give some example about the physical properties in which the inverse square law is applicable. For example, the first one is gravitational field, the second one is electric field, third one light, and fourth one is sound. We can see one by one. And one more thing is, this geometrical law will be able to find the ability to understand the inverse square law very precisely. Now let us see one of the physical property, that is gravity. So this will obey in general the inverse square law. For example, let us consider the earth's surface. The distance of the earth's surface from its core, let us consider r. If we find the gravity at the surface of the earth, it will be the same in three-dimensional direction. That's why if you write the acceleration due to gravity, then g will be equal to 4 pi capital G capital M divided by 4 pi r square. What is capital G? That is gravitational constant, and M is the mass of the earth. 4 pi get cancelled and acceleration due to gravity g is equal to 1 by r square. It will come. That is gm by r square. Gm is constant. So we can tell that the gravity is inversely proportional to the gravity is equal to gm by r square, where g is the gravitational constant and m is the mass of the earth. Both are constants. So we can write g is proportional to 1 by r square. Since it is inversely proportional, the gravity decreases with increase of the distance from the core of the earth. That's why it obeys the inverse square law. Now let us see the next physical property, the electric field. This electric field in general it obeys the inverse square law. To understand this, let us consider a point charge and the electric field produced by the point charge. This electric field will be spreading like a growing sphere. So if we find the electric field at any point from the point charge, then it depends upon the distance of the point from the point charge. So S is the strength of the point charge. If you write the intensity, I is equal to S by 4 pi r square, where 4 pi r square is the surface area of the sphere and S is the charge strength. So instead of this constants, if we put proportionality symbol, then I is proportional to 1 by r square. The intensity of the electric field is inversely proportional to square of the distance between the two charges. That's why this physical property, electric field, will obey the inverse square law. It is clearly explained by Coulomb's law. That means that the force of attraction or repulsion between the two point charges will be directly proportional to the product of the two charges and inversely proportional to the square of the distance between the two charges. This case belongs to the two point charges. If we consider a single point charge and if we travel far away from the charge, the intensity of the electric field decreases due to the point charge. Now let us see the applicability of this inverse square law for electromagnetics. That means that electromagnetic radiation. For this, let us consider an example. Consider an incandescent lamp at a point and we can fix that. Now from the incandescent lamp, the electromagnetic radiation is just spreading in three-dimensional direction. If we find the intensity of this electromagnetic radiation at different distance, it will be different. It shows that the distance of the point from the incandescent lamp increases, then the electromagnetic radiation intensity will decrease. If the distance is twice, then the decrement will be 1/4, and if the distance is thrice, it will be 1/9. Let us consider the next example, solar spectrum. How the solar spectrum we are getting? Because the sun is a very large pair of very hot gases. The core of the sun is very dense, and if you travel towards the surface of the sun, and it is less dense. The core temperature of the sun is 14 million Kelvin, and the surface temperature of the sun is 6000 Kelvin. From the core of the sun, it is emitting electromagnetic radiation. That is, it is acting as a black body emitter. Then the electromagnetic radiation, when it approaches the surface, it is giving line spectrum. Why it is giving line spectrum? Because in the surface, the materials are less dense. That is, the chemical elements present at the surface will be very less dense. But at the core, it will be dense. From the dense, if you measure, it will be giving continuous spectrum, and at the surface it is giving line spectrum. The elements that will be appearing at the surface will absorb a particular wavelength, and the observed wavelength of the radiation will be appeared as black lines, that is called Fraunhofer lines. That's why from the surface of the sun we are getting line spectrum. This is also obeying the inverse square law. That means that from the core, if we travel, we are getting only line spectrum instead of continuous spectrum. To ascertain the validity of this inverse square law, let us do an experiment with the radioactive source. Consider the radioactive source cobalt-60 and GM counter, Geiger-Miller counter. In the Geiger-Miller counter, at the base we can keep the radioactive source, and we can measure the radiation coming out from the radioactive source in two different directions, in horizontal as well as vertical direction, with 5 different measurements with a time interval of 2 minutes. Let us do that. If we do that, then we can plot the graph. We can find the intensity of the radiation at different times. If you see that the distance of the receiving electrometer from the base increases from the first distance and the second distance, the intensity goes on decreasing. And one more thing is, if time proceeds, then for every 2 minutes the intensity decreases with increase of the distance. So if you plot a graph, the intensity goes on decreasing like this. After doing the experiment, let us plot a graph between the intensity of the radiation against the time interval. If you see that the intensity goes on decreasing with respect to the time. Since we have measured for every 2 minutes interval with respect to the distance, the intensity goes on decreasing. It is an exponential curve. So this is a proof for inverse square law. We came to the end of the session, and I hope you understood about the applicability of the inverse square law to various physical properties. I gave all this with an example. In the upcoming session, we are going to see about electric potential. Thank you.